we have done a few parts here. Let me explain a bit of these things to you. Okay, and then you can either watch the lecture or get the notes. Okay, so in solid state, first of all, I started with a cube because cube is a particular entity that we will be facing many times in this chapter in solid state chemistry. So I wrote a few things about the cube, corners, edges, and faces. These things you already know, right? There are 8 corners, 12 edges, and 6 faces. But there is a new term that is diagonal. Now in this we can see that there are 2 types of diagonal. Each face will have 2 diagonals, right, Hamza? Each face will have 2 diagonals, and there will be body diagonals as this one. If you can see this is a body diagonal. So we will have 4 body diagonals and 12 face diagonals. And if the edge length of the cube is a, then face diagonal has the length a root 2 according to Pythagoras theorem. Okay, according to Pythagoras theorem. So what will be the edge length, Hamza, for face diagonal? A root 2. Okay, each face diagonal will be a root 2. Okay, just memorize this one part, and you can also see that we have proved how it is a root 2 because the edge length is a, and the body diagonal will be a root 3. Okay, are these 2 things fine, Hamza?
Yes, sir.
Okay, face diagonal is a root 2, body diagonal is a root 3. A root 2 and a root 3, just memorize this one. Say in your head 5 times right now. Face diagonal a root 2, body diagonal a root 3. Face diagonal a root 2, body diagonal a root 3. Okay. See, in your sleep also, if somebody asks you what is the face diagonal, what is the length of face diagonal, you will say a root 2. And what is the length of body diagonal, you will say a root 3. Next is a few things. For example, why we are studying this cube? Because the atoms that we are going to study will be present in some parts of this cube, and we will be arranging them. We will be having this type of many cubes, and they will be making solids. Okay, they will be making solid. So a few terms, for example, if the atom is present in the corner, excuse me, if the atom is present in the corner of the cube, okay, and at that time when it is present in the corner, its contribution is 1/8. Its contribution is 1/8. Okay, if I get any chance to explain you how it is 1/8, I will explain that, or you can watch the lecture, anything will work. But right now you have to memorize this, that there are, how many corners are there? 8 corners, and the contribution of each is 1/8. Okay, so please remember this one value, 1/8. And if the atom is present in face center, I can explain this face center one quite easily. You are sitting in a cuboidal room, right, Hamza? Yes, Hamza, you are sitting in a cuboid type of room, or cube type of room.
So currently in a cuboid.
Cuboid type of room. Okay, that will work. So you look at one of the walls, that will be the face, right? If you assume it to be and approximate it to be a cube, then one of the walls will be the faces, right? Yes or no?
Yes, sir.
Okay. Now, if you look at those walls, that wall is shared by 2 rooms, right? Each and every wall is shared by 2 rooms, correct?
Yes, sir.
Right. So if I place an atom inside inside a wall, that means inside the face center of a cube, then that atom will also be shared by both rooms. That means in one room there will be half atom present, right? In one room there will be half atom present, correct?
Yes, sir.
Similarly, corner is shared by 8 rooms. That is why its contribution is 1/8. And if some atom is present in the center of the body, center of the whole cube, then its contribution is 1. And if it is in the edge center, its contribution is 1/4. Its contribution is 1/4. These are the things that you have to remember. These are the things that you have to remember. Okay. Now moving on to the next thing is some voids. Okay. Can you see that here we have 3 atoms I have placed, and in center we have got a vacant space, and vacant space are called as void. Okay, vacant space are known as voids. Okay. Then we have here this triangle, and hence it is named as triangular void. This is named as square planar void. Okay, triangular void and square planar void. Then in 3D we have tetrahedral void, cubical void, and octahedral void. Okay, so these are the voids that you have to study first, so that you can easily identify them if you come across them. Okay, if you come across them later. Now we started with 1D packing. That means we are packing in one dimensional way. We are packing and keeping the atoms in one direction only. So I started with one atom and I proceeded in this direction, and I start keeping atoms. So I got 1D, I got 1D packing. And coordination number of the atom, it just means that how many atoms are touching the center atom, how many atoms are touching the atom which is present, not in the corners, but the middle ones. Okay, but the middle ones. So the coordination number is 2 because each of these atoms are touched by 2 different atoms, right? 2 different atoms. So what is coordination number? Coordination number means how much atoms is touching it, how much atoms is touching it. Then when I went to 2D packing, I had a choice that I can put the atoms under atoms or I can put the atoms in the depression. So when I put atoms under atom, I got AAA type packing. When I put atoms in the depression, I got ABAB type packing. Okay, ABAB type packing. Now further on, I wrote a few points. For example, the coordination number in AA type will be 4 because each atom is touching 4 atoms. ABAB type will be 6 because each atom is touching 6 atoms. And the void here is square planar, as you can see. See, the void, it is made by 4 atoms and the midpoints of those atoms are making a square. And here we are getting a, oops, sorry. Here we are getting a triangular void. Here we are getting a triangular void. Okay. Now next thing is the unit cell. So there are we are trying to study this solids. So rather than studying the whole solid like this, what should we do? We should take a part of solid that is a unit, and if that unit is repeated many times, then we will get the whole packing. So essentially, we are studying a small portion of the packing and generalizing it towards the whole packing. So this yellow one is the one unit cell that you can take. There can be many unit cells. For example, this red one is also a unit cell. This rectangular face one is also a unit cell. But the unit cell that we will be studying is the yellow one. Why? Because this unit cell is also showing me what is the coordination number of atoms. What is the coordination number of atoms? Similarly, the unit cell in ABAB type that we will be taking will be a hexagonal shape, in hexagonal shape. Since it is a square shaped unit cell, we name it square close packing, and it is hexagonal in shape, we name it hexagonal close pack. Is this clear, Hamza and Rishan, for both of you? Yes or no? You will get more clarity if you watch the lecture. Okay, but for now, we can proceed for now. Okay.
Yes, sir.
Okay, we will be dealing with 2D packings only right now. So let me just take a few things. Okay. Now, and to ask a few things. Darshan,
Yes, sir.
what is the length of phase diagonal?
Phase diagonal A root 2.
A root 2. Krishna, what is the length of body diagonal?
Sir, A root 3, sir, or 3 root A.
A root 3, not 3 root A. Never 3 root A.
Oh,
Okay?
yeah, yes, sir. Okay.
A root 3, only A root 3. Okay. Sarah, what is the contribution of edge? What is the contribution of edge center atom? The atoms which present in edge?
1/4.
1/4. Okay, very good, very good. Okay, fine. Now we are done with 2D packing. We have seen what type of arrangement is there, ABAB type, AAN type. Now we have to tell which of this packing is better. So in 2D packing, we have two choices. Now, please remember, 2D packing will always be imaginary because our world is 3D. But let us suppose if 2D packing was there, then which would have been preferred, AAA type or ABAB type, which would have been preferred. So for this, we have a concept which is very important. It is known as packing efficiency. It is known as packing efficiency. Okay, how good is the packing? Okay, how good is the packing? That means how good is the solid. If I want to compare any two solid, I will be looking at packing efficiency. Okay, so it is very similar to when you compare two students, right? So how will you compare two students? What will you see? If you want to compare two students, what will you see? Tell me, guys. Yes, Krishna, Darshan, Hamza.
So marks.
Marks, very good, है ना? marks, or you will see the percentage of marks that it is getting. Okay. So this is also very similar to marks only. It is, see, if I take the unit cell has atoms. That means those atoms will be solid, and there are vacant spaces which will not be solid, right? So atoms are the marks obtained. The area that is occupied by atom, the space that is occupied by atom inside the unit cell is the marks obtained divided by the total area of unit cell, or total space occupied by unit cell into 100. Okay, very similar to marks, very similar to marks. So if I want to compare to a student, I will look at the marks. If I want to compare to solids, I will be looking at packing efficiency. So it is space occupied by atoms in UC. What is UC? What is UC?
Unit cell.
Unit cell, very good. Divided by total space occupied by unit cell into 100. Okay, into 100. There is another term which is very similar to packing efficiency. It is known as packing fraction. Okay, it is known as packing fraction. So it is packing efficiency without the 100. Okay, just packing efficiency without the 100. So you will get a fraction. If you compare this, you will get a fraction. Now there is another term which is known as void percentage, which is equal to 100 minus the packing efficiency. Okay, 100 minus the packing efficiency. So please write this down. Let me know if you're done. Just need to start writing from packing efficiency. Okay, this part. You can write also one more thing, that packing efficiency is equal to packing fraction into 100. Okay. Any doubts still here? Guys, any doubt? Darshan,
No, sir.
Rishan, Hamza? No? Okay. By the way, Ramzan Mubarak to all of you guys. Okay. Sara must have kept her first fast today, right?
Yes, sir.
You're in India, right? Okay. The others, Hamza and Rishan, they must have kept it yesterday.
Yes, sir.
Okay. Hamza, are you also leading the Taraweeh?
Not yet, sir, but from today I will, because I was in Makkah. So the first Taraweeh was in Makkah, and second was like the half day I was on my way back to Riyadh, so I couldn't prepare for it.
Acha, acha, acha. Okay, okay. So who is leading the prayers in Makkah? Like when you were praying?
The first eight rakat was led by Sheikh Yasir al-Dosri, and
Okay.
the second imam was Sheikh Abdurrahman al-Sudais.
No, I lost you after share.
The second imam was Sheikh Abdurrahman al-Sudais.
Okay, fine. So this.
Yes, sir.
So you were in Makkah. Did you pray for me?
Yes, sir. Obviously, like you said, so I remembered that.
Thank you. Thank you. Jazakallah khair. Okay. Please raise your hand if you're done. Okay. Krishna is done. Darshan is done. Waiting for Rishan, Hamza, and Sara. Okay. Hamza is also done. Sara is done. Okay. Rishan is also done. Okay, fine. So now what we will do, we will first of all calculate the packing efficiency of AAA type or SCP. Okay. So please don't write anything. Just listen. square closed packing. Okay, square closed packing in 2 dimensions. So I will take the unit cell from here. And paste it here. Okay. And I know I don't need a few atoms, that these are the atoms that I don't need. Okay. So we have this as our unit cell, and we want to find the packing efficiency, that is the space occupied by atoms divided by the total space of. So let me write here packing efficiency, which is equal to space occupied by atoms divided by space occupied by unit cell into 100. So space occupied by atoms, right? Space occupied by atoms. So what I can do, rather than writing the whole thing, what I will do, I will write number of atoms into the, now since we are talking in 2D, this is a circle, this circle will have a area, right? So into area of one atom divided by space occupied by unit cell. So we know that this edge length is how much? It is A, and since it is a square, the area will be, space will be what? Area of unit cell, which is a square, which will be equal to A square, right? So I can directly write here A square. Now, here we have number of atoms. Number of atom is written as Z. It is dignified and it is denoted by the letter Z, number of atoms in unit cell, into the area of one atom will be equal to pi r square divided by A square. So the first item that we have to worry about is the Z. What is the Z of, what is the Z of this unit cell? What is the number of the exact number of the effective number of atoms in the unit cell, right? Any problem till here in Z pi r square or the area of unit cell as A square?
No,
guys?
sir.
No, no? Okay, fine. This is A. Now let us first of all find the Z. Okay, so Z of square closed packing in 2D. Now, whenever you want to find Z, you will first of all see and identify the types of atoms. The type of atoms with respect to their positions. So in this we can see that we have 2 types of atoms. All of you can see that in this unit cell I have 2 types of atoms. Yes or no? Can all of you see that there are 2 different types of atoms? There are atoms which are present in the corner, and there is one atom which is present inside the unit cell, right? Yes or no?
Yes, sir.
Yes, sir.
Okay. So what you can say, there are 2. You will write here in the corner. Please remember this is a square, okay? Corner, and there is one in the center. Now, since center one is completely present inside the unit cell, its contribution will be 1. Is that clear? Yes or no?
Yes, sir.
Yes.
Okay. But when I look at the corner atom, please remember this is not a cube. This is not a cube. This is 2D. So in 2D, I have a method in which we can calculate the contribution, which is known as the angle method. If you remember 3D, that is cube, we use the sharing method, right? In how many rooms is the atom shared, or is the corner shared, or is the face center shared? But in 2D, we have an angle method. So first of all, you tell me how many atoms are there in the corner? How many atoms are there in the
4.
corner? 4 atoms are there in the corner into the contribution of each, and it will give me the effective number of atoms in the corner. So for the contribution, what I will write? I will write the, now this is the corner, right? What is the angle of the corner? What is the angle here?
90 degree.
90 degrees.
90 degree. Okay. And what is the complete angle if I go like this? Tell me.
360.
360. So 90 by 360 is the contribution of each atom. And this will give me 90 to 4, and 4 in 1s are 4. This will give me 1, and for the center I have 1, and this will give me 2, right? Hence the z is equal to 2 for square close packing in 2D. Is that clear? Yes or no? Please tell me.
Yes, sir.
Yes, the z is very clear. Okay, fine. Don't worry. Don't write right now. Now what we will do, we will put inside here the value of z, that is equal to 2 into pi. Okay, now there is something that I always forget, but I remember it in the last. I have to multiply 100. And I have to multiply here also 100. This will be equal to 2 into pi r square divided by a square into 100. Now we are seeing a problem. You can see that even if I substitute the value of pi as 3.14 or 22 by 7 and multiply this by 100 into 2, we do everything, but still we are left with two letters here, right? Two letters, R and A. We don't know the value of R, we don't know the value of A. I'm giving you guys 2 minutes and you will tell me how should we tackle this problem. How should we tackle this problem? I need a number as a percentage. Now, you must have never heard the marks of any student in terms of any variable. There is always a pure number, a pure percentage. So we also want a pure percentage in the packing efficiency. But we are having a problem that we don't know the value of R and we don't know the value of A. So guys, take 2 minutes. Think how should we tackle this problem? This is not a chemistry problem. This is a mathematics problem. Okay. Yes, any idea? We have to eliminate R and A. How should we do that? How should we do that? Okay. If I find a relationship between A and R, okay, what should I do? I should find a relationship between A and R and then substitute the value of A in terms of R. For example, let us suppose I got the relationship A is equal to 2R. Then what I can do, I can remove this A and I can put the R, a 2R here, and then we can cancel the R square into an R square. And we will be eliminating both the variables. Is that right? Yes or no?
Yes,
You
sir.
understand the funda now? All of you understand the funda now? How should we deal with this?
Yes, sir.
Okay. Now, if you see the relationship between A and R, so let me erase this part here and make some space for relationship between A and R. Hamza, Sara, Rishan, all of you understood this now?
Yes.
Yes, sir.
Relation between A and R. Okay. Now, if you look at this part here, this is a phase diagonal, yes or no? This is a diagonal of square, correct?
Yes, sir.
Right, guys? Okay. And if this is A, this is also going to be A, right? And what will be this value? What will be the value of this diagonal here? What will be the value?
So A
A
root 2.
root 2.
Very good, है ना? A root 2. And we know that this length will be R. Then again, this length will be R. This length will be R because this is the center, radius. This again will be a radius. And you can see what is the relation. The relation is A root 2 is equal to 4r, and you can write a is equal to 4 by root 2r, and then we can substitute this value here. So I will write 2 into pi into r square into 100 divided by a is 4 by root 2. So 4 square root 2 square r square. So r square and r square will cancel out. And here we have root 2 square, which will be giving me 2. So this 2 and this 2 can be cancelled. And you will get what? You will get pi upon 4 4s are 16 into 100. Did I miss anything? I hope I did not. Okay, so please calculate this. Yes, Krishna.
No, sir. I was done. That's why I just.
Okay. Did I make a mistake somewhere? Should be pi root 2 square. Okay. Sorry. Yeah. Wait a second. आप लोगों ने भी ध्यान नहीं दिया, हमने भी ध्यान नहीं दिया. I was worried because I remember it is pi by 4. This is r square. So r square and r square can get cancelled. It will be actually 2 into pi by 4 by 2. Now, so this 2 will go here, right? This 2 will come up in the numerator, and it will be 4 into pi divided by 16. This will make it pi by 4 into 100. Okay, pi by 4 into 100. Just correct that. So I did a mistake while cutting. I should not have cut these two numbers. Okay. So you have to find the value, exact value, okay, the percentage, and then send me in the chat. Tara, when is Maghrib in Patna?
Around 6:10.
Around 6:10. Okay, fine. 6:40, 6:45 is fine for you, है ना?
Yeah.
Okay. Please send the answer in chat. 5/4 into 100. Okay. Now, those who are giving answers, let me show you something. You would not believe that this question was asked. Can you see that it is the same unit cell, right? And this question was asked in JE 2010. Okay, the same question. So if you have done this, then you can directly answer that D is the correct answer. 78.54% is the packing efficiency. Okay, so these are the small things. Now student they ask, sir, ये important है क्या? 2D solids तो होते भी नहीं ना. Like you do never have 2D solid in real life, but still it was asked in JE examination. Okay, so please remember, everything is important. Okay, everything is important. Fine. So let me erase this part here and erase this part. Okay, so next things that you have to write is what is the packing fraction, which will be equal to 0.78. You can write. Then you will tell me what is the void percentage. What is the void percentage? So I hope you know, guys, remember void percentage is 100 minus the packing efficiency. Then the answer void percentage, guys. What happened? Six. Yeah, correct. 21.46%. Okay, very good. So now, please raise your hand if you're done writing it. Okay, or if you're not done, then please start writing. If you have already written all of this, then raise your hand. Darshan, Krishna, and Sara, you guys got the assignment?
No, sir.
No, sir.
No?
No, sir.
Acha. All of you have registered in the app or in the website
Yes.
anywhere?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. You should have got the assignment. Fine, I will check. Please raise your hand if you're done writing, okay? Waiting for Rishan and Hamza. Waiting for Rishan. Rishan, please raise your hand if you're done. I don't know whether he's here or not. Okay. Now, see, once we have seen that, we have to calculate the Z for each and every unit cell whose packing efficiency we want, and we also need to calculate the relationship between A and R. So when we are going to calculate the packing efficiency of AB type, that is HCP, packing efficiency of AB type, that is HCP in 2D, hexagonal close packing in 2D. So first what we will do, we will calculate the Z and relationship between A and R, okay? So let me take the unit cell from here and then start working with it. Oops, I lost 2 atoms. Here. Yeah, so this is our packing. First of all, we will calculate the Z for hexagonal close packing in 2D. What is the Z? Okay. So here also, how many types of atoms are there? Tell me.
2, sir.
2 types of atoms. What are the 2 types?
Corner and center.
Corner and center. So for the center one, we can directly write the contribution as 1. How many corner atoms are there?
6.
6. And what will be the angle in each of these corner? What will be the angle?
60 degree.
Yes, 60 degree. It is greater than 90, na? I think you can see it is greater than 90, right? See, 90 होता तो यहाँ रहता. It is greater than 90, na?
Yes, sir.
120.
Yeah, it is 120 degree, na? So 120 divided by 360. So you can see that this is 12 3s are This will be 6 by 3, which is equal to, oops. You can also do 3 into 2 is 6, so this is 2. So we will get the Z is equal to 2 plus 1, which will be equal to 3. Okay.
So we should do
Now,
divided by 360, sir.
yeah. See, if I ask you, I will tell you why. If I ask you what is the angle here, 360, na?
Yes.
So 360 by 360 gives you 1. And if you're having a part of the atom, then you will have to look what part is present. So the whole is 360, and this whole atom, it is 360. And what part is there? 120 of 360 is there. Okay, so that is the angle method. You have to 120 divided by 360, which will give you 2. Okay, this will give you 2. And from the center, you will get 1. So this is the Z. Z is equal to 3. And next is we have to look at the relation between A and R. So these are the prerequisites. These are the things that we require in order to calculate the packing efficiency. Now, let us see. This is the A edge length, right, guys?
Yes, sir.
And we also see that this is R and this is R. So A is equal to 2R. A is equal to 2R. This is the relation between A and R. Please don't write these things. Now let us go on and calculate the packing efficiency. So the packing efficiency, it will be equal to Z into pi R square divided by what will be the area of hexagon? Can anyone tell me what will be the area of hexagon? Okay. Look, what I can do, I can divide this whole hexagon into triangles, into different triangles. Let me erase this part and show you guys. I hope you can see that I have made 6 equilateral triangle, right? Yes or no?
Yes, sir.
6 equilateral triangle. What is the area of equilateral triangle? Heron's formula. I think it is Heron's formula. I don't remember exactly.
So root 3 by 4 A square.
Yeah, correct. Yes, correct. Pi R square divided by area of unit cell will be, there are 6 triangles, hence 6 into root 3 whole divided by 4 R square. Okay, R square. This is the formula for the area. Then you can cancel R square, and you can simplify further, right? You can simplify further. Okay, and you can also put the Z as 3. So let us put the Z as 3. You can also eliminate 3 and 6. You will get 2 here. Then you can further eliminate 2 by 2. You get 2 here, and this will be equal to this 2 will go above. You will get 2 pi divided by root 3 into 100. You
So
need to
shouldn't it
substitute
be
the
2R square, sir? Root 3 by 4, 2R square.
2R square what?
So the area of the triangle, sir. Since we told that A is equal to 2R.
Yeah, sorry, I put A square, R square here, no? Yeah, thank you. This will be A square, no? Okay. Wait a second. I wrote there R square rather than A square. Okay. It will be equal to 2 into pi R square divided by area of unit cell. It will be equal to 6 into root 3 by 4 A square into 100 equal to 2 into pi R square divided by 6 into root 3 by 4 into A square. This will be equal to 4R square, right? This is what you were telling now? Correct.
Yes, sir.
Yeah. Now you can solve this. Now you can solve.
So Z should be 3, right?
हाँ, ये हम तो too many mistakes for a day. This is Z only, हाँ, ये 2 नहीं है. This is Z. Guys, yeah, approximately correct, Krishna. So you can also don't write this answer. I will give you the exact answer. I think because of approximation, there is slight difference. Waiting for others. Okay, root 3 is how much? What is the value of root 3?
So 1.73.
Yeah. Okay. For those who don't know, 1.73. Yes, Sarah. Okay, waiting for others. Darshan, Hamza, Rishan, what happened? Yes, Darshan, Rishan, and Hamza. क्या हुआ? Where are you having difficulty? This will be approximately 90.68. Okay. 272 कैसे मिल रहा है आपको? Wrong, Hamza. 100 से ज्यादा कैसे हो सकता है? Pi is 3.14. 2 into 1.73. If I take even 1.7, this will be 3.14 divided by 3.4 something. So obviously numerator is smaller than the denominator, so it will be less than 1. Okay. If you multiply it by 100, you will get some value, but you will always get less than 100. This will be 90.68. फिर से कीजिए please. Okay. Packing fraction you can write 0.9, and void percentage you can write. What will be the void percentage? 329, 9.32 percentage. Write this down. Let me know if you're done. Done. All of you done?
Yes.
Please raise your hand. Raise your hand. Especially Hamza, Darshan, and Rishan. Okay, I think Rishan is not. Okay, Rishan is here. Fine. You can lower your hands. Okay. So which is a better solid? Which is better solid? AB type or AA type? Tell me. Which is better?
So AB.
AB type is better solid, है ना? Write this down with me. AB type packing in 2D is a better packing than AAA type. Okay. So if you get any questions such as write the differences between square close packing in 2D and hexagonal close packing in 2D, then what are the points that you will write? First of all, you will draw the picture, right? Secondly, you will identify the type of voids. Thirdly, you will identify the coordination number of atoms. How many atoms are touching each other? Okay, in AA type and ABAB type. Next is you will tell me what is the packing fraction, packing efficiency, void percentage. Okay. Fifth item that you will write is the Z. Okay, Z for both the cases. Sixth, you will write the relation between A and R. Okay. Then seventh, at last, you can write the what is the unit cell. Okay. So there are 7 points of differences that you can write for SCP and HCP. And if you write in and remember even 5, that will be fine. Okay. Yes, Rishan, you want to say something? No. Okay. Fine. Now, since we are done with 2D, let us move on to 3D. So if you remember, I started with 1D and I went to 2D. And in 2D, I found that I can have 2 different types of structure. I can either have square close packing or I can have hexagonal close packing. Now, if I move on to 3D from SCP, so my base layer will be the square close packing, that is AAA type, and we are moving to 3D structure. Then also what you can see that I can have 2 different types of arrangement. So if I show you guys, this is the square close packing, right? This is the square close packing. Now, if I take one atom and I want to put another atom, so I want to put this red atom in the next layer that is on top of this layer. This is the first layer, the black layer is the first layer, and the next layer that I want to put is the red atom. So I can either put it on the atom that is the black atom, or I can put it in the void made by the red atoms. Yes or no?
Yes.
Can you see the 2 arrangements, right? So if I want to move from SCP to 3D, then also there will be 2 different possibilities, and we are going to learn about both of them. We are going to learn about both of these arrangements. Okay. So what I will do, let me write the topics. 3D packing. This is clear, right? If I have the base layer as a square close packing and I want to put another layer, I can have 2 different arrangements. Yes or no? Sara, Darshan, Hamza, all of you are with me?
Yes.
Okay, fine. So 3D packing. So after we have square close packing, we are moving to 3D. And in 3D, we will have 2 different types. Atoms on atom. And the other will be atoms on void. So let us look at atoms on atom first. Atoms on atom. Okay, just give me 2 minutes, okay? Okay, fine. So atoms on atom. Let me get this packing here. So you also start making this with me, okay? Since I am making it, and when I start discussing it, then you can leave your pens, okay? It sometimes gets a bit tricky. Okay, this is good. It is somewhat good. Then I will take this whole thing here. I will place this whole atoms on top of the black one. Okay, so when I'm putting it on it, when I'm putting this red one on the black one, then you can see, but after I am done with this, you can't see it, right? So I will just move it a bit like this. Okay, so you can see that the red ones are placed on black ones. And please remember that the shape of the black one and the red one, these are not circles. Now they are spheres because we are dealing with 3D structure. Is that clear? Yes or no? Please tell me. The red and the black, all of these are spheres. Okay, all of these are spheres because we are dealing with 3D atoms. Now what I will do, I will take a section of this part, and I will make a unit cell out of this. Okay, I will make a unit cell out of this. So as you can see that the lower layer is made up of black atoms. I will place 4 black atoms in the lower layer, and I am giving them a type of angle so that it is visible in a better way. And on top of each black one, I will have red atoms. So these are the midpoints of the black atom and the midpoints of the red atoms that you can see. Then what I will do, I will join them. Okay, join the black one. And I will join these atoms also like this. Okay. So I think you can see that I have got a unit cell now, right? This unit cell is what? This unit cell is cubical unit cell. Yes or no? Can you see that it is a cube?
Yes,
Yes
sir.
or no, guys? Tell me. Right? This is a cube. Okay. Second. Label it like this. Red, 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 and red. What about others? Sarah, Hamza, Rishan. All of you can see that this is a unit cell which is red, which is
Yes, sir.
a cube. Okay, so we have got a cubical unit cell. Those who were present in the last class, tell me what is the void? It will be a 3D void now. What is the void here? Array, what happened? Those who were present yesterday, which void is there?
So cubical void.
Very good. सारा पढ़ाई नहीं हो रही है, cubical void. हाँ सारा,
Yes, sir.
भूल गए आप cubical void? भूल गए. Okay. Now, next is we want to write. Okay. First of all, you tell me. Since the red atoms are placed on black atoms, I can say that all of these layers, whatever we are putting, these are indistinguishable, and hence I can also say that this packing will also be known as AAA type packing because all the layers are similar AAA type in 2D. Please remember that this red and black, these are just colors for you to distinguish the different layers, okay? But these are all indistinguishable in real case. AAA type in 3D. AAA type in 3D. And we can see that unit cell is simple cubic and it is also AAA type in 3D. The void is cubical void. Now, we will calculate the Z for simple cubic unit cell. Simple cubic unit cell, okay? Now you tell me, you have to look at this particular unit cell and tell me how many types of atoms are there in terms of their placement, in terms of their position. Where are all the atoms present? All the atoms are present in? All the atoms are present in corners. Very good. All atoms are in corner. All atoms are in corner. Now, if they are all in corner, how many are they? There are 8, and each contribution will be 1 by 8, and hence the Z will be equal to 1. Is this clear? Yes or no?
Yes, sir.
Z is equal to 1 for simple cubic. Now let us move on and let us look at the relation between A and R. So as you can see that this whole length here this is A and this part is R and this part is R, right? Yes or no?
Yes, sir.
All as we can see, right? And hence the relationship between A and R is very easy. It is A is equal to 2R. A is equal to 2R. Okay. So all of you, please start writing. Let me know if you're done. Raise your hand if you're done. Okay. Ashwin is done. Sarah is done. Krishna is also done. Waiting for Rishan and Hamza. Just waiting for Hamza now. Okay. Now, moving towards the packing efficiency. Packing efficiency of simple cubic. Okay. So packing efficiency, it will be equal to Z into, now you tell me, since it is a sphere now, so what is the space occupied by sphere? It will be area or volume? Area or volume? Guys, this will be area or volume. These are spheres now. So space occupied by sphere will be
Volume.
Volume, na? Yes, yes, yes. Volume. कितना time लग गया आप लोगों को? So what is the volume of one sphere? What is the volume of one sphere? ये भी नहीं याद. 4/3 pi r cube. Okay. And what is the unit here? What is What is the unit cell, guys? What is the shape of unit cell? What is the shape of unit cell? अरे इसके देखिए बताइए ना इसको. Yes, Darshan, Hamza, Sara, Krishna, what happened? What is the shape of unit cell? हाँ,
It's a
Krishna.
square planar.
अरे यूनिट सेल लिखा हुआ है हमने क्यूबिक बाय स्क्वायर प्लेनर. ये तो आपको नहीं दिख रहा होगा यहाँ पे बिकॉज आई एम शोइंग दिस अबव फेस हियर. ओके, तो 3D में दिखा नहीं सकते ना कि क्यूब यहाँ पे बन रहा है. कैन यू सी दैट आई हैव मेड अ यूनिट सेल? दिस वन इज अ यूनिट सेल.
Yes, sir.
ओके,
Yes.
okay, unit cell is what? Simple cubic, and hence ये आप लोगों को फिर से हम लिख ही देते हैं ठीक से ताकि आप लोग भूलिए नहीं बिल्कुल. पैकिंग एफिशिएंसी हैज ओनली वन फॉर्मूला. द फॉर्मूला इज space occupied by, please complete with me now, space occupied by
Atoms in unit cell.
atoms in unit cell divided by total space occupied by unit cell into 100. Space occupied by unit cell will be equal to the number of atoms inside unit cell into the space occupied by one atom, and one atom will be 4 by 3 pi r cube divided by space occupied by unit cell. The unit cell is a cube and its volume will be a cube into 100, and we know that a is equal to 2r. Hence we can write this as z is also what? 1. Z is 1 into 4 by 3 pi r cube divided by 2 cube into r cube, and r will get cancelled into 100. Please solve this. Let me know the answer in chat. What is the packing efficiency? So essentially you have 4 pi divided by 3 into 2 cube into 100. Got one answer, I think. Yes, Sarah. Correct, Krishna. Okay, fine. 3 answers I have gotten now. Sarah, Krishna, and Hamza. काफी जल्दी सबने दे दिया आंसर. Yeah, correct. I think if you calculate it with calculator, it is 52.4. You guys are getting 52.33. Okay, yeah, 52.35. Okay, fine. This is equal to It is actually 359. So this will be 52.359. So this will be 36, and then you can write 52.4. Okay. Essentially, you will see that many books writing 52.4 and not 52.3. 4%. You can write packing fraction is equal to 0.52. Okay, by the way, packing fraction is also known as packing factor. Okay, and the void percentage will be how much? What will be the void percentage, guys? What is 7.6? Just write this down. Let me know if you're done. Then, guys, yeah. Okay. Waiting for Darshan and Rishan. Darshan is done. Okay. Waiting for Rishan now. Okay. So see, we have studied a few things till now, Hannah, that you have to remember. You have to always remember. What are the things that you have to always remember? Face diagonal, body diagonal. Okay. Then in face center, what is the contribution? Edge center, what is the contribution? Corner, what is the contribution? And then in body center, what is the contribution? So face diagonal is a root 2, body diagonal is a root 3. Face center has the contribution of half, edge has the contribution of 1 by 4, corner has the contribution of 1 by 8, and the body has the contribution of 1. Okay. So that means if the atom is present in face center, it will have 1 by 2 contribution, edge center will have 1 by 4, corner will have 1 by 8, and the body will have 1. And you have to remember 2D voids. There is triangular void and there is a square planar void in 2D. And in 3D, there are 3 voids. There is a tetrahedral void, there is a cubical void, and there is a octahedral void. These are the things that you have to remember. Okay. Now, next is we did packing. So in 1D packing, there is only one question that can come. Coordination number is equal to 2. Then I move on to 2D packing. And in 2D packing, we have two different cases. We have cases in which we have SCP, square close packing, and HCP, hexagonal close packing. Square close packing has the packing efficiency of 78.4, and HCP has the packing efficiency of 90.6 and 90.6 or 7. Now we further moved on and we did 3D packing in SCP. When I moved to 3D from SCP, I saw that I have two different cases. There is a case in which we will have atoms under atom, and I will get simple cubic structure. This simple cubic structure, it had the packing efficiency of 52.4%. And then we will get another structure that we will talk about later. Okay, so these are the things that you have to remember. Please keep revising it. You will not forget anything from this chapter because everything is sequential. If you start from here, you can bring and you can make this ladder on your own, and then you don't have to remember and by heart these things. Okay, the only things that you have to by heart are these parts, and these parts are to be by hearted because it will make your life easy.